Welcome to all of you. Now we discuss Unit-1 2021 Biomathematics, Semester 5 Mathematics Honors, University of Calcutta. Question paper 2021 Unit 1. Question 2a. State the basic assumptions of Bruce Birdworm population dynamics and construct the model equation with logistic population growth and suitable prediction term. Derive the corresponding dimensionless equation. Basic assumptions of Bruce Birdworm model are the growth of the birdworm can be represented by the logistic growth model in absence of the predation of birdworm. In absence of ddt of n equal to Rn bracket 1 minus n by k, where n is the density of birdworm at time t, k is the carrying capacity of the environment, r is the intrinsic growth rate of birdworm. Number 2, the rate of predation of birdworm depends on n and can be taken as Holling type 3 functional response given by Pn equal to mn square by a square plus n square, where m positive is the maximum removal rate of birdworm due to predation and a positive is the half saturation constant. Because when n equal to a, put here n equal to a, we get Pn equal to m by 2. So this is called half saturation constant. Incorporating such predation term 1, the growth rate of birdworm may be represented by ddt of n equal to Rn bracket 1 minus n by k minus mn square by a square plus n square, equation 2. Third assumptions, we neglect the growth of predator, that is bird, and host far and approach, as these occur at slower time scale in comparison to that of the birdworm. Next part, non-dimensionalization. We introduce 4 non-dimensional quantities given by x equal to n by a, t dash equal to m by a t, p equal to a by m r, q equal to k by a. So from 2 we get ddt of ax equal to this using these terms, non-dimensional terms. After simplification we get omitting prime, replacing t dash by t. So we get ddt of x equal to px bracket 1 minus x by q bracket close minus x square by 1 plus x square, equation 3. Note that a and k have same dimensions as n, r has dimensions time inverse, and m has the dimension n into time inverse. Next question 2b. Consider the following epidemic model. Ddt of s equal to a minus rs minus beta si by 1 plus alpha I, and ddt of I equal to beta si by 1 plus alpha I minus mu I. A, r, alpha, beta, mu are positive parameters, and find the equilibrium points of the system and discuss the nature of the equilibrium points. Now for equilibrium points, we know ddt of s equal to 0 equal to ddt of I, and hence we get a minus rs minus beta si whole divided by 1 plus alpha equal to 0, and from ddt of I equal to 0 gives beta is by 1 plus alpha minus mu bracket I equal to 0. From the second equation we get either I equal to 0 or beta is by 1 plus alpha minus mu equal to 0. When I equal to 0, from the first equation we get, put I equal to 0 in the first equation, so we get s equal to a by r. And when beta is by 1 plus alpha minus mu equal to 0, and this from this, that is when beta s minus mu by alpha equal to mu I, and from the first equation we get this a minus rs minus beta s I by 1 plus alpha I. So put here beta is 1 plus alpha equal to mu, put here this mu. Now this mu I equal to, from simplification we get mu I equal to beta s minus mu by alpha. So putting the value of mu into I, so we get a minus rs equal to beta s minus mu by alpha, and from this we get s equal to a alpha plus mu whole divided by r alpha plus beta. Now beta s whole divided by 1 plus alpha equal to mu gives this 1 plus alpha equal to beta s by mu. So this implies 1 plus alpha equal to beta by mu into this s equal to this. So put here a alpha plus mu whole divided by r alpha plus beta, putting the value of s. So alpha equal to this and I equal to a beta alpha minus mu r alpha whole divided by alpha mu bracket r alpha plus beta. Hence the equilibrium points are E naught this a by r comma 0. This is the value of s a by r and I equal to 0. When I equal to 0, we get s equal to a by r. So E not equal to a by r comma 0, and E star equal to, that is we call it a star. A star equal to this a alpha plus mu by r alpha plus beta, and I star is this a beta alpha minus mu r alpha whole divided by alpha mu bracket r alpha plus beta. For existence of E star, we must have this beta alpha minus mu r alpha must be positive, because other terms are positive. So we get this a beta by mu r greater than 1. That is r0 greater than 1, where r0 equal to a beta by mu r, called the basic reproduction number for existence of E star, this equilibrium point E star. Now let f is a function of s and I equal to a minus rs minus beta si by 1 plus alpha I from the given differential equation. This and right hand side equal to f function f, and from the second equation is called g function g function of si. So del del s of f equal to this, del del I of f equal to this, del del s of g equal to this, del del I of g equal to this. The Jacobian matrix J for this system, we get fs, fi, gs, gi, and so we get this 2 by 2 matrix this. Now for this equilibrium point E naught, so value of j equal to this matrix J reduces to this, put here s equal to a by r and I equal to 0. This I equal to 0, s equal to a by r, and put here. So we get this 2 by 2 matrix minus r minus a beta by r 0, a beta by r minus mu. Obviously this is the upper triangular matrix, so these eigenvalues are diagonal elements, this minus r and negative, and this a beta by r minus mu this. Now eigenvalues is negative, clearly this minus r is negative, but if this is negative, that is a beta by mu r is less than 1, that is r0 less than 1, then the DGP equilibrium, DGP means I no infected, that is I equal to 0, because E naught this I equal to 0, so this E naught is called DGP equilibrium, DFE, DGP equilibrium. E naught is locally asymptotically stable if R naught is less than 1. So epidemic will not occur if R naught less than 1. And next equilibrium point E star, for at this point E star, J bracket S star comma I star, so this equal to minus r minus I star mu by S star minus mu square by beta star mu I star by S star minus mu alpha I star by 1 plus alpha I star. Now beta star by 1 plus alpha I star equal to mu, and this is we get already we get this beta s by 1 plus alpha I equal to mu. So this actually this is A star, actually this is the I star. So we get so this is the matrix 2 by 2 matrix to study this stability of this Jacobian. This trace of this J is sum of the diagonal elements, this plus this, so this is obviously less than 0, and if I is feasible, that is if R naught is greater than 1, because this I star is feasible when R naught is greater than 1. Already we have deduced this this star existence, this feasibility that is biologically meaningful if I star this is positive. So this is, if this is positive, I star is positive, that is means this numerator is positive. That means r naught greater than 1. So this of the second case, this r naught greater than 1. Now determinant of j at this point a star I star equal to this, and this by Routh-Hurwitz criterion, this determinant j is positive and res j is negative. And if a star I star is visible, that is if r naught greater than 1. Hence this endemic equilibrium E star, this star is called endemic equilibrium, is locally asymptotically stable if r naught is greater than 1. Next question 2c. Write short notes on the following: number 1 Gompertz growth, and number 2 basic reproduction number. Gompertz growth, the Gompertz growth law given by ddt of n equal to rt nt, this r is a function of t, n is a function of t time, where nt is the size of the population at time t and rt is the growth coefficient, and is given by ddt of r equal to minus alpha, where alpha positive is the decay coefficient. From 2 we get rt equal to r naught e to the power minus alpha t, where r naught is the initial growth rate. Using 3 from 1 we get ddt of n equal to r naught e to the power minus alpha t nt, equation 4, and this is the Gompertz growth equation. From 4 we get dn by n equal to r naught e to the power minus alpha t dt. Integrating we get log to the base e, that is ln n equal to r naught by minus alpha e to the power minus alpha plus c is the integrating constant, and when initially when t equal to 0, n equal to n naught say, then c equal to ln n naught plus r naught by alpha, that is ln n by n naught equal to r naught by alpha bracket 1 minus e to the power minus alpha t. So n equal to n naught exponential this bracket r naught by alpha bracket 1 minus e to the power minus alpha t bracket close, equation 5. This is the required solution of the equation 4, differential equation 4, and is known as Gompertz function. Next, basic reproduction number. Actually, this is the unit 2 in the new syllabus. The basic reproduction number is defined to be the average number of new cases produced by a single infected individual in a completely susceptible population, and this is denoted by r naught and is the dimensionless number. This r naught is proportional to infection by contact, and contact by time by infection, that is r naught equal to tau c bar into d. Tau is the transmissibility, that is the probability of infection given contact between a susceptible and infected individual, and this is the c bar, tau c bar. C bar is the average rate of the contact between the susceptible and infected individuals, and d is the duration of infectiousness. In the SIR epidemic model, r naught equal to beta by nu, where beta equal to tau into c bar, this, so the effective contact rate, and nu is equal to d inverse, that is the removal rate. If r naught less than 1, then the DGHP equilibrium point is stable, and if r naught greater than 1, the endemic equilibrium point is locally asymptotically stable. Next question 3a. Consider the growth model ddt of n equal to rn bracket n by a minus 1 into bracket 1 minus n by k, where r, a, k are positive parameters and a is less than k. Determine all the equilibrium points and discuss their stability. For equilibrium point n star, we know ddt of n at the point n star equal to 0. So r n star bracket n star by a minus a 1 into bracket 1 minus n star by k equal to 0. So we get n1 star equal to 0, n2 star equal to a, and n3 star equal to k. So there are 3 equilibrium points. Let ddt of n equal to fn, then fn equal to rn bracket n by a minus 1 into 1 minus n by k. Now f dash n equal to this. Now stability analysis for this point, first equilibrium point n star equal to 0. So f dash n1 star equal to 0 gives this minus r. N1 star equal to 0, put here n equal to 0, so this 0, only we get this term, n 0 only we get this minus r. R is positive, so this is less than 0, so n1 star equal to 0 is locally asymptotically stable. For n2 star equal to a, f dash n2 star equal to a equal to r into bracket 1 minus a by k. Obviously this is positive, since it is given that a is less than k, that is a by k is less than 1. So n2 star equal to a is unstable equilibrium point. Now third equilibrium point, n3 star equal to k, f dash n3 star equal to k equal to minus r bracket k by a minus 1, which is less than 0 because k is greater than a, that is k by a greater than 1. So this third equilibrium point, n3 star equal to k, is locally asymptotically stable equilibrium point. Next question 3b. Consider the following harvesting model. ddt of n equal to rn bracket 1 minus n by k minus qen, where E is the fishing effort, Q is the catchability rate, N is the stock level, R is the growth rate, K is the carrying capacity. Investigate the stability of the equilibrium points and show that the maximum sustainable yield is Rk by 4. If n star be an equilibrium point, then ddt of n at the point n star equal to 0. So we get r n star bracket 1 minus n star by k minus q e n star equal to 0. So we get this n1 star equal to 0 and n2 star equal to k into bracket 1 minus q e by r. So there are two equilibrium points, n1 star and n2 star given by this. Let fn equal to the right hand side of this equation. So r n minus n square by k bracket in minus q e n. F dash n equal to r bracket 1 minus twice n by k minus q e. Now stability analysis for this point, n1 star equal to 0, f dash 0 equal to r minus q e. The equilibrium point n1 star equal to 0 is locally asymptotically stable if r minus q e is less than 0, and unstable if r minus q is greater than 0, that is if r is greater than qe. And for the second equilibrium point, n2 star equal to bracket 1 minus qe by r into k, and f dash into star equal to this, after simplification we get qe minus r. Therefore n2 star is locally asymptotically stable if qe minus r is less than 0, and unstable if qe minus r greater than 0, that is if qe greater than r. Next, second part, the maximum sustainable yield. The sustainable yield at n2 star is y equal to qe n2 star. Y equal to qe n2 star, value of n2 star is this 1 minus qe by r into k. So we get qk bracket e minus qe square by r. dde of y is equal to qk 1 minus 2 qe by r. d2y de square equal to minus qk into 2q by r, that is equal to minus 2kq square by r, which is less than 0. The optimum value of y, we have dde of y equal to 0. This implies e equal to r by 2q. Now second derivative, at this point e equal to r by 2q, this equal to negative minus 2k by r q square is less than 0. So y is maximum at this point e equal to r by 2q. Hence the maximum sustainable yield y max, y value is this qe into star, this this value. So q into value of e equal to this q into this r by 2q minus 1 minus q into k into 1 minus q by r to r by 2q, y max is this, y equal to q e into k, q e value is this k into 1 minus q e by r, 1 minus Q E, E means this, by R, this. So we get RK by 4, the answer. Next question, 3B, sorry, 3C. Consider the following comparative model: ddt of x equal to x bracket 1 minus x minus alpha y, and second equation ddt of y equal to rho y bracket 1 minus y minus beta x, where alpha, beta, rho are positive constants, so that if alpha greater than 1 and beta less than 1, the first species is going to extinction and second species will surviving with its carrying capacity, but the opposite phenomenon occur when alpha less than 1 and beta greater than 1. For equilibrium point x star y star, we get this equal to 0, this equal to 0, and this x null clines, this ddt of x, this we have x star equal to 0 and 1, or 1 minus x star minus alpha y star equal to 0. And from 1 null clines, ddt of y at this point x star y star equal to 0. So either y star equal to 0 or 1 minus y star minus beta x star equal to 0. Choose x star equal to 0, then from 2 we get this y star equal to 1. So we have two equilibrium points here, 0 0 and 0 1. If we choose y star equal to 0 from 2, then from second equation 1 we get x star equal to 1. So third equilibrium point x star y star is 1 comma 0, and solving 1 minus x star minus alpha y star equal to 0 and 1 minus y star minus beta x star equal to 0, we get x star equal to this, y star equal to this, if 1 minus alpha beta not equal to 0. Thus we get 4 equilibrium points: E0 0 0, E1 1 0, E2 0 1, and E star 1 minus alpha by 1 minus alpha beta, comma 1 minus beta by 1 minus alpha beta. And for feasibility of E star, this 1 minus alpha by 1 minus alpha beta must be 0, greater than 0, and 1 minus beta by 1 minus alpha beta must be greater than 0, which is possible only when this alpha is less than 1 and beta is less than 1, or number 2, alpha is greater than 1 and beta is greater than 1. Hence, coexisting equilibrium point, this interior equilibrium point E star, does not exist if alpha is greater than 1 and beta is less than 1, or alpha is less than 1 or and beta is greater than 1. Now to find the Jacobian matrix, set F equal to this and G equal to this, the right hand side of the given equations are this, and we find the partial derivatives, del x of F, del y of F, del x of G, del y of G, and hence J Jacobian matrix, this 2 by 2 matrix, this we get this. Now stability test for the trivial equilibrium point E0, value of matrix J is given by 1 0 0 rho. The eigenvalues of 1 and rho both are positive, so E0 is unstable node. And for E1, that is J at the points 1 0 is this minus 1 minus alpha 0 rho into bracket 1 minus beta. So the eigenvalues are minus 1 rho into 1 minus beta. If beta is greater than 1, then both eigenvalues are negative, and E1 is stable node if beta is greater than 1, and saddle point, that is unstable if beta is less than 1. And this E2, equilibrium point E2 at the point 0 1, Jacobian J at this point 0 1 is this 1 minus alpha 0 minus rho beta minus rho, this lower triangular matrix. So the eigenvalues are minus rho and 1 minus alpha. If alpha is greater than 1, both eigenvalues are negative. So E2 is stable node if alpha is greater than 1, and saddle point unstable if alpha is less than 1. And conclusion that for the case 1, if alpha is greater than 1 and beta is less than 1, then E0 unstable, E1 unstable, E2 stable, and E star unfeasible. Hence, for this case, the first species X star is going to extinction and second species Y star will surviving with the carrying capacity. And this corresponding page portrait is this X, Y, and this corresponding 1 minus x minus alpha y equal to 0, 1 minus beta x minus y equal to 0, this E2, and this 1 minus 0 comma 1 by alpha, and this E0, E1, this point E1, and this E2, point E2. So this is the stable, and this E0 and E1 unstable. Actually, we draw these two straight lines using this condition. Case 2, if alpha is less than 1, beta greater than 1, then E0 unstable, E1 stable, E2 unstable, and E star is unfeasible. And so in this case, the first species will be surviving to its carrying capacity, and second species will going to extinction. And for this case, we draw these two curves, the straight lines, this using this. So this is the E0 unstable, E2 0 1 unstable, and E1 1 0 unstable for this case. And this completes the Unit 1 2021. Thank you for watching this video.